Moving forward in chapter 6, we want to talk about atomic radius.
All right, so we have learned so far that all these ideas about where electrons are around atoms, and that motivates the periodic table, right? Electrons have this sort of building up in their configurations, and that leads to the patterns that we see in the periodic table, where we have the atoms where the highest electrons are in the S subshells or D subshells, P or F, and those correspond to particular blocks. And the size of those subshells corresponds to the size of those blocks, the number of groups across. So there's this pattern. We can see that the periodic table is following these patterns and trends in filling these subshells. That's based on all these, Pauli principle, Aufbau principle, and all those sorts of ideas. So one of the important things is, we have we talk about these blocks because all we care about is that highest subshell, right? Those highest electrons, what is, that last electron you put in. That's because those valence electrons are the electrons in those highest energy shells. Those are the electrons that are actually on the outside of an atom. Those are the ones that actually are doing chemistry. When an atom interacts with something else, for say this antimony over here, all of these core electrons don't really matter. Those are just all buried in. It's these handful of these valence electrons on the outside. If I have another atom that comes and interacts with this antimony, it's going to interact with those 5 electrons. So it's really the valence electrons that drive chemistry. And so, the reason why we organize the periodic table like we do is that a single column in the periodic table, all of the atoms in that column have the same number of valence electrons in the same types of subshells. And what that means is that if they have the same types of valence electrons, and valence electrons determine chemistry, then all the atoms in a group have similar chemical properties, right? Our alkali metals, column 1 of the periodic table, they all have a single valence electron in an S subshell. It may be the 2s, 3s, 4s, 5s, 6s, and so on, but it's all the same type. So they're going to have similar chemical properties. Okay, and so this is the whole point of why the periodic table has the shape that it does. It's all about describing electrons, and that those patterns of electrons give us the sorts of similar chemical properties for everything that has that same pattern. We've seen this when we looked at ions, and we saw that we look at these patterns of ions, these electrons determine chemical reactivity, and we know that for atoms in a given column, they form the same types of ions, and the reason why they form that is because atoms tend to form ions that have 8 valence electrons. Those 8 valence electrons are the octet. We know for a noble gas that looks like this, where it can be different shells on down the periodic table, but 2s2, 2p6, say for neon, 3s2, 3p6 for argon as we go on, this idea. And so we know that there's patterns in the ions that atoms tend to form, and we can explain that based off the electron configuration, because these octet of electrons tends to be stable because we call that a full valence. There's no unpaired electrons in the valence shell. All right, so what we want to talk about is following these ideas, that ions form, we can predict them based on locations of the periodic table and following patterns and properties of electron configuration. And so, we can see that that's a chemical property that is determined by the electron configuration of atoms. And because the electron configuration varies in the periodic table, we would expect that other properties are going to vary across the periodic table in predictable ways. Right? The whole idea of the periodic table is that there's a trend in how things are varied, or how properties vary. And so we want to look at these, and we're going to call these sorts of trends periodic trends. So there are plenty of properties that vary across the periodic table, but not in a predictable way. What we want to look at are things that vary in predictable ways. And what that means is that they're determined basically by the change in properties of these different, of the different electron configurations for my different atoms. So in order to look at trends, we first need to define some properties. So the first property of atoms that we want to look at is going to be the size of atoms. So we call this the atomic radius. So we know that atoms are not hard spheres, but they are roughly spherical-ish, and they tend to have a certain size. So they're not necessarily going to have a hard, if we think about like, billiard balls where they hit on their edges, and that's going to be a specific size. Atoms are going to be a little squishy, right, because it's electrons just taking up space on the outside. So they will be a little soft, and they're going to change in size under different situations. But overall, atoms will have some sort of characteristic kind of average size or the rough approximate size. And one of the things we do know is they are very small. So we know that all of our atoms we would expect to be very small. So, this we can see here I have chlorine and carbon atoms that are, a couple, just over 100 picometers apart. That is 10 to the negative 12 meters. So these are very, very small. And so one of the things I also want to note is that we're going to be looking at individual numbers, the size of an atom. We're going to give them a radius, right? The distance from the center out to the edge of the sphere. But it's important to note that we're kind of looking at some sort of average description of an isolated atom. But really, if you put atoms into molecules, their size is going to change a little bit. So there is some variation, but overall, we're looking at a characteristic size. And really of these isolated atoms as best as we can kind of measure experimentally or figure out.
Atomic radius certainly is going to vary from one atom to the other. So the question is, what determines the actual size of the atom? And so the first thing is going to depend on just the size of the orbital. So the edge of an atom is going to be based on whatever the highest energy orbitals, whatever the highest orbital, those valence orbitals are on the atom. And so what we can do to count that is look at the highest principal quantum number of orbitals on an atom. And so we can see, for example, that lithium would have 2 as its highest, n equals 2, sodium is n equals 3, and potassium is n equals 4. Those are literally just larger orbitals. So as a result, we can see that the atoms get bigger and bigger as that number goes up. So we can see that on the periodic table, we know that the shell, that highest shell, is going to vary. It increases down a group. We can see lithium, sodium, and potassium. That's group 1A, just going down. And so we can see that this is changing. As we go down a group on the periodic table, we get to higher quantum numbers, and we'd get a bigger, we'd expect to find larger orbitals and therefore larger atoms. One thing to note, this does not change across a period. So this is one factor that affects size. It doesn't change on a period. Next to lithium would be beryllium on the periodic table. And we can see that just is the same. They're both n equals 2. So there's got to be something else that affects our size within a period. And so to look at that, we want to look at the number of protons in the nucleus. We can imagine that the orbitals contain electrons, right? And the whole reason why electrons are on atoms is because that puts them close to the positively charged protons. And so the more protons there are in an atom, in a nucleus, there's more positive charge, and the electrons are going to be more attracted to that nucleus, and they're going to contract. And so what that means, we know that size is determined by shell. You get some sort of average or kind of relative size. But the number of protons in the nucleus can cause that to kind of contract. So this nucleus right here has some protons. This would be for, say, beryllium. You have 4 protons. You're in the n equals 2 state for those electrons, and they're held kind of tightly. If we go up to oxygen, there are now 8 protons in that nucleus. It's still n equals 2, but because there's more protons, they end up contracting. Those orbitals get a little bit smaller. They get a little bit closer to the nucleus. And so we can see that if we look at this idea of increasing protons, we would expect that there's more positive charge as we go down a group and across a period from left to right. So there'd be more positive charge. We would expect for the overall effect to be a shrinking of the radius.
Put these together, I can get an overall trend of how atom size changes across the entire periodic table. And we're going to focus mostly on the main group. So that's the combination of the S and P blocks of the periodic table. The D block has similar trends, but they're a little harder to see much smaller differences. But if we look just at the main group, we can see that going across a period, generally when we think about going across a period, we would think about going in this direction because that's how atomic number increases. And if we do that, we would say that orbitals get smaller because there's more protons. This is for a given period. It's the same principal quantum numbers, so say 1s and 2s in period 2. And so you're not changing the size of the orbitals, you're just adding more protons as you go across. So therefore they're more tightly bound, the electrons are more tightly bound, and your orbitals are contracting, they're getting closer to the nucleus. So the size decreases as we go across a period. We usually still talk about trends in the ways in which they increase. So what we say is from right to left, the size increases. So it's kind of counters to how we usually read English letters, but we say that, from right to left, that's the arrow that's on the slide, the size of atoms increases. Then for our groups, going down a group, we get the increase in orbital size. That causes just atoms to get bigger. So really this is that principal quantum number increases, the orbitals just get bigger. We did say that there's more protons as you go down a group, right? There are more protons, so there's going to be that attraction is going to pull those in. But when it comes down to it, that increase in the principal quantum number outweighs it. So really we can say that as we move down a group in the periodic table, electrons are just in orbitals that are larger, they are further from the nucleus, and our atomic size will be larger. So what that means overall is the smallest atom is helium. So helium would be in the top right corner of the periodic table. It is basically on the low side of both trends, meaning that it is the smallest atom. The other corner is francium. And so francium is the bottom alkali metal, and that is the largest atom that we have. Here we can see actual experimental results of atomic sizes. And we can see our trends, increasing atomic radius from right to left and increasing atomic radius from top to bottom. And overall, this is the main group, so we can plot out our S. We've kind of skipped the transition metals, would be somewhere in between here, but we can get all of these radius, and these radiuses are plotted in picometers. So again, 10 to the negative 12 meters, so atoms are really small. But one of the important things is we can see that the size of different atoms does vary quite a bit. You will notice francium, our largest atom, isn't on here. It would just be slotted right beneath cesium there, but it would be a little bit bigger than cesium. But one of the things we can see even with this, helium is only 31 picometers in a radius, whereas cesium is 265. So that's much larger. There's a full almost order of magnitude difference in the size of these atoms. And so it really does matter. These atoms, the atomic sizes, they're all still very small, but we can see that some of them are much smaller than each other. Cesium is much, much bigger than helium, and so that's going to matter in the long run in affecting the overall properties, kind of the physical aspects of this atomic size. And, we do care about this atomic radius. This does matter. The size of atoms, the size of atoms affects the sizes of molecules, because bigger atoms, when they combine together, make bigger molecules. So, we've seen things like our diatomic molecules, they follow these trends. And so, we have these nice trends of diatomic molecules, the variable sizes. As atoms get bigger, the molecules get larger. So, and if these are plotted, almost we can see the sizes, they follow these periodic trends. And so, oxygen is to the right of nitrogen. So oxygen atoms are smaller in the periodic table. So as a result, oxygen molecules are smaller. And it's kind of, you got two oxygen atoms. So that molecule is kind of doubles down on oxygen being a smaller atom. Overall, O2 is a even more smaller molecule. And so this, you may be familiar with the fact that, the idea of putting nitrogen in your tires, pure nitrogen, because it's better than air. And the motivation behind that is really that nitrogen molecules are bigger than oxygen molecules. And so they're going to escape less. You can think of a rubber molecules, your tire rubber is basically a bunch of like tangled cords. So, if you think about like the wires under your desk or something, that there's that kind of tight-knit mesh, and, it would take some time for something to move through there. And these gas molecules, we know, are randomly moving. They can make their way into that kind of mess of rubber and permeate out of the tire. And because nitrogen molecules are larger, the atoms are just physically bigger, it's harder for them to kind of fit through that tangle of wires that we have there and make their way out. So the motivation behind putting only nitrogen in your tires is that it would take more time for the gas to escape, so you'd have more stable tire pressure. I'm not necessarily advocating that you should use nitrogen, but that is at least the mechanism. We can understand why that would be important or beneficial over oxygen. Oxygen's a smaller molecule, so it can escape faster. I'm not sure this graphic from someone selling nitrogen does seem to imply that oxygen is leaving really fast, and I'm not sure that that's true, but nitrogen certainly does escape more slowly because they're just bigger molecules. So they stay in your tire doing their job of inflating the tire. All right, so we know that these trends are, have some importance. The size of atoms matters. So what we want to do is be able to kind of look at a set of atoms and figure out their trends. It's not important for us to be able to know the sizes of atoms. We don't want to memorize them or kind of know anything like that. What we do want to be able to do is look at, say, a series of atoms and figure out which ones are the biggest and which ones are the smallest. What's kind of the relative ordering of all my sizes. And in order to do that, we're really going to be asking, well, how are they related on the periodic table? This is a periodic trend, so we would expect these atoms to have, if we know how they're related on the periodic table, we can figure out how their size is related. And because, once we know how they're related, what's the trend for that direction? So I have AT, BR, CL, F, and I. If I want to look for these on the periodic table, they are the halogens. So this is astatine, bromine, chlorine, fluorine, and iodine. And so they're all over on the period on the that right side in column 7A, group 7A. And so, I want to ask, well, for this, if they're in a group, I only care about the relationship of atoms in a single column. How do these trends change up and down the column? And we know that size increases down a group. For fluorine, it is in group or period 2. Right? And then so that means that's a 2s and 2p. Chlorine is 3s, 3p, 4s, 4p, 5s, 5p, 6s, 6p. So that means that astatine is going to be the largest simply because it has its electrons in the highest shell. They all have the same type of valence electrons and the same type of orbitals. The only difference is the size of those orbitals. So we know that fluorine will be the smallest, then chlorine, then bromine, then iodine, and astatine is the largest.
Participation 623, question 2. Arrange the following atoms in order of increasing size. SB, RB, XE, and SN. This is the second question on participation 623, due Tuesday, June 23rd at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, arrange the following atoms in order of increasing size. It's antimony, rubidium, xenon, and tin.
The periodic trends are defined for columns and for periods, right? Groups and columns, periods, rows, right? But we're not always comparing atoms necessarily in that sort of direction, kind of perfectly. And so, a lot of times, the periodic table is 2D, and we want to understand the relative size of things that aren't related so cleanly. And so what we're going to do is we're going to use kind of the corners. So we know that francium in the bottom left corner is the biggest, and helium in the top right corner is the smallest. And so overall, the trends kind of move in the same way in those two directions. And so overall, we can say that elements that are closer to francium are larger, and elements that are closer to helium are smaller. Kind of overall, that kind of, you think of a gradient across the periodic table in those two dimensions. And what we're going to do in order to kind of quantify that is by counting blocks. So counting on the periodic table how many horizontal and vertical moves. So you can kind of think about the periodic table as a grid, and you can only move up or across, up, down, and then left, right, not diagonal. But you can kind of quantify diagonal distance using that. So for aluminum, for example, blocks from helium, it's 7. So you have to move up 2 and then over 5 in order to get to helium. And so that corresponds to, overall 7 moves across the periodic table, 7 blocks. Whereas for oxygen, you have to move 3. That's over 2, up 1. And so that corresponds to it being closer. And then selenium is 5. So selenium is over 2, up 3 to get to helium. And so, you're overall counting these number of moves. So what we would say is because oxygen is the closest to helium, it's the smallest, then selenium, and then aluminum. And so it's all of this kind of, strategies for kind of combining these together. Now, you will note that when you're counting blocks, you can lead to some fringe cases. Oxygen is 3 blocks away. Well, so is chlorine, which one's bigger. In general, if you want tiebreakers, the group moves, up-down moves, are more of a size, but really we're not overly concerned with those sort of fringe cases. Oxygen and chlorine are pretty close in size, and so we're not necessarily overly concerned with, well, which one is the tiebreaker. If you do need to break ties, moves up and down cost more. They lead to larger increases in size or changes in size because you're going to that higher principal quantum number, which is a bigger effect. But we're really more focused on the
Okay, we had a participation question. Yeah, a bit of a drought there, but we found our second question in this video. A couple more videos to go. See you in the next one.